So the direction of electric field is outwards. So for point P, electric field is towards right, and for point P dash, the electric field is towards left in the directions as shown. Now next step is to imagine a small area dA. If you take area dA here at the plane end, then the direction of area vector is along the outward drawn normal. So we'll get area vector in the direction as shown. If you take small area dA here, then the area vector would be towards left. Why? Because the direction of area vector is always along the outward drawn normal. What if we take area on the curved surface like this? If we take small area dA on the curved surface, then the area vector dA would be in upward direction. And if you draw the same area here, the area vector would be downwards. Now, here at this particular point on the curved surface, the direction of electric field is towards right, but area vector is upwards. So from this we can say that for plane ends, E and dA, they are parallel to each other. That means the angle between them is 0. Hope you know scalar product or flux phi equal to E dot dA. So cos 0 is 1. So flux through plane ends exist. For area vector dA on the curved surface, area vector is upwards, electric field is towards right. So this angle is 90. And everyone knows that cos 90 is 0. So here the contribution to the flux due to the curved surface is 0. But it exists only for the two plane ends only. Now continuing. Let a thin conducting sheet of charge. Remember, it's a non-conducting sheet. That was my mistake. Let a thin non-conducting sheet. Now when I say non-conducting, it means when we give charge to it, the charge resides at its place. It never changes its position. The sheet is infinite in extent and having surface charge density sigma. Unit is coulomb per meter square, charge upon area. Let P be the point at a distance small r from the sheet at which electric field intensity is required. Let us choose a point P dash symmetrical to P on the other side of the sheet. To find field at P, we draw an imaginary Gaussian cylindrical surface cutting through the sheet such that the points P and P dash lies at the plane ends. And the area of each plane end is capital A. Here, suppose the total area of plane end is A and this is also A as well. Now since the sheet is of infinite extent, the electric field E is normal to the sheet directed outwards on both sides. Now here the flux through two plane ends. Remember, for point P and P dash, value of area is same. So we'll take phi suffix E equal to surface integral E dot dA plus surface integral E dot dA. First is for P, second is for P dash. Now for area at the two plane ends, the angle between E and dA is 0. Cos 0 is plus 1, cos 0 is plus 1 in each case. So we'll have EDA cos 0, EDA cos 0, EDA, EDA. Electric field is constant for points lying close to the sheet. So we have phi suffix E equal to E taken out, integral is applicable to dA only, plus E out, integral for dA only. And this dA integration changes to area A because the area of plane ends is capital A. So we'll come up with EA plus EA, that is phi equal to twice EA. Now here we have to apply Gauss theorem as well. So for that we need charge enclosed by this Gaussian cylinder. Now how to get that? First of all, we'll check the area of the sheet which is present within the cylinder, and this area is again capital A. Now here sigma is charge upon area. So the charge which is present in area A is the charge enclosed. So we have sigma equal to Q upon A. So from this we'll say Q equal to sigma A. So when we apply Gauss theorem, charge enclosed Q is equal to sigma A. Now the flux through curved surfaces vanishes as vector E and dA are at 90 degree. This I have already explained. Everywhere on the curved surface. Hence the total flux through Gaussian cylinder is the flux through plane ends only. Now by Gauss theorem, phi suffix E equal to Q upon epsilon naught, where Q is the charge enclosed by Gaussian cylinder. Just now I explained Q equal to sigma A. How? I have already explained it to you. So using this Q in above, we come up with phi suffix E equal to sigma A upon epsilon naught. This is equation number 2. Now comparing first and second, we come up with twice EA equal to sigma A upon epsilon naught. Rearranging, we'll get E equal to sigma upon 2 epsilon naught.